Okay, so with this video, I want to get a couple things taken care of. Um, First, the distinction between physical and chemical properties, and then in section 3.6, physical and chemical changes. So properties versus changes. They're related, but there is a difference between the two, and I sort of want to get at that a bit. I'm going to skip through these slides. They will be available to you. They're a good set of notes for you, and they do talk about a few examples. And like here, it gives you a nice, condensed place, if you will, where it's just the key features from the text. So, but again, I'll probably skip over and just hit the highlights and point out those key things to focus on. Okay, well, let's see. Let me just highlight something here real quick. The issue about physical properties. Notice this idea without changing composition. Boiling of water, freezing of water, water still water after those processes take place. That's a physical property. Okay, a chemical property would be something if you put electricity into water, you can cause it to form hydrogen gas and oxygen gas. So in chemical, if you're measuring chemical properties or you're describing a chemical change, then the composition is changing of the molecules. And I'll go through a little bit more. Well, I'll do this. I'll go through, what does it look like, really? What does it look like from a perspective of the graphics in our textbook versus what is it going to look like in more of a chemical reaction, something that would be more likely that you would see on the test. And again, the PowerPoint slides, just briefly, like gasoline can be talked about in two different senses. If a physical property would be the odor or the gasoline, or the color of the gasoline, or the fact that the gasoline is a liquid at room temperature. The chemical property of gasoline, one would be flammability, right? We all know it's flammable. It burns. And I guess you could even say that a chemical property is the fact that, it's poisonous in high concentrations. Don't drink it. That would be an example of something that could illustrate its chemical property. Anyway, so let's take a look. So physical property, and that's the one I'll focus on first. This coffee pot, this tea kettle. It's you have water down here, and like I've said before, I like how Tro uses his graphics. In that water, you have these little molecules floating around, and these little H2O molecules, and we can symbolize them either H2O or H2O in this fashion. This has got a Lewis structure, or we can, if we have graphics, then we can do these space-filled models. In the boiling process, the addition of heat, the molecules start to vibrate and translate, move around faster, and eventually they're going to acquire enough energy from that thermal energy to then transition into the gas phase from the liquid phase. Okay, that's a detailed way of saying the water is boiling. And that is a phase change. That is going from a liquid state to a gas state. And so phase changes are a common example of physical properties. Now, I want to take that a little bit further and tag it with physical change. So really, physical change, the way Tro is breaking up these topics, that's dealing with section 3.6. Is where the change issue gets into play, or in this case, no change is probably the better way to say it. And so let's talk about these different things in front of us. So boiling point, melting point, density, and let's just use water as our reference point here. It's a real common reference point on the Celsius scale, which is the scale that we'll use, and we'll talk about the details of the temperature scales in one or two videos from now. Boiling point of water is about 100 degrees Celsius. It's a little bit lower in Asheville since we're at about 2,300 feet. Melting point of water is 0 degrees Celsius or 32 degrees Fahrenheit. Density of water is 1 gram per milliliter. Actually, the density of water is used as our reference point for density, or I guess maybe more specifically something called specific gravity, which only occasionally pops up for our class. But essentially density is there is a distinction between the two, but it's not important here. And again, these are all describing physical properties. I can measure the boiling point of water, the melting point, or the density of water, and at the end of that process, at the end of quantitating those values, I still have water left over. I don't chemically change the water molecule. Now, to represent that in a very concise statement, then this is where our chemistry language comes in real handy. That is a very specific statement. And I'm going to add one other little guy here, this little triangle. When you see the little triangle, that means that you're to add heat, or to heat something. You're going to add heat to this sample to get it to boil away, all right, to get it to that 100 degrees Celsius, so it does that rapid transition between liquid and to gas. But notice at the end of the day, I still have water molecules, just a phase change has occurred. L is going to be used to indicate a liquid, G for a gas. Melting point. What does that describe? Well, that's simply a solid, S. But still, you're going to apply heat to it, and it's just a simple phase change going to a liquid. At the end of the day, you still got water. It's just in a different phase. Now, density, there's actually no phase change associated with density, but when I measure, well, what does density mean, right? We did this in lab. First lab was safety, second lab is what I'm thinking of, the first real lab. Density and volume. We had to take the mass of the water on the scale. We had to then measure the volume of the water with the graduated cylinder, divide the two, and you have your density value. After that experiment was done, the sample that was still in the graduated cylinder was still water. So no changes occurring with those molecules. Now, so state changes. Let me actually add this to this slide here. So really, we're talking about phase changes. When we talk about physical change, it's phase change. I guess in some ways, technically, physical change for density would be not applicable, to tell you the truth. So anyway, we're talking about phase change when we're describing physical change of a substance. And every substance has this. I mean, some substances will decompose before they boil, and some substances will undergo sublimation, which, we saw this in lab, or we will see this lab, and depending on when you're viewing this video. Solid iodine, which is a dark purple solid. If you add heat to it, it doesn't go to the liquid state. It goes to the gas state. That's sublimation. So that's another example. Dry, solid carbon dioxide that you can buy at the grocery store. It is an example of something that will do this phase change as well. But again, at the end of the day, even though it looks different, you got this purple gas in the test tube, it's still just iodine, and it's still, if you cool it back down, it'll go back to the solid. That's called deposition. Okay, so we see no changes in the molecule. Well, let's look at chemical versus a physical change now. And again, something I've already stated. So physical change is not its composition. So the matter does not change its composition. Whereas for a chemical change, matter does change its composition. And let's look at just a couple examples. I guess one, if we just read through this example that Tro is providing, copper turns green, like an old penny that has primarily copper in it can, you see sort of a green tinge to it, or in some cases it has more noticeable reaction with air. And that is an indication of a chemical change. We have now converted the copper to one of the copper salts through that process. Now, if we zoomed in on the process, again, the graphics here are pretty good. if we think about an iron nail, nice array, regular array of iron atoms. From the previous video, we would call this a pure substance, elemental form. And then just over time, we know what happens to iron. It rusts. The reaction of iron and oxygen gas helped along a bit with water. That certainly assists the process. Then notice what happens. Now we don't have just a single atom in our array. We have some other things there. In this case, the little red spheres are oxygen atoms. Now we have a chemical compound. We have chemically modified our sample here. That is an example of chemical change, or the way Tro is trying to say here is that chemical property is sort of the descriptive process that's going. The iron rusts. If I wanted to talk about the chemical change, I would write out a chemical reaction. I'll do that for some other examples here in just a minute. We can also look at these are the same graphics that are in the textbook. Physical change, a little simple lighter like this. Butane is a liquid down here. It's just a small hydrocarbon. It's related to gasoline. It's related to it's more closely related to propane, like liquid propane in barbecue tanks. Anyway, if I just open the valve, this is a liquid down here because it's under just a little bit of pressure. If I open the valve, it allows the gas to escape. And notice if you compare that structure and that structure, they look the same. And you don't even need to know about what the details. There's actually 4 carbons attached in a row here, and there's hydrogens and all the spots that bonds are needed to what we say complete the octet or complete the valency for carbon. We'll talk about that at a future date. But all we have to recognize now is like, oh, the molecule looks like this now and this now. And we're going from a liquid to a gas. This is a phase change. The molecule does not alter its structure. Now look at the example if I then strike the fuel and air mixture that is formed here. Compare the molecules, much different. And we don't even need to know, really, I mean, even if these labels weren't here, we should be able to view it and say, oh, well, this molecule looks like this, and now it looks much different. There's actually some red in here where there wasn't red before. Remember, the red are the oxygen atoms from the oxygen gas. It's in the air. We're forming water vapor, and then these are structures of carbon dioxide here. This is an example of chemical change. It burns. Now, if I want to talk about more detailed structure, and let's do that with this little layout here, just like I did for water. Let me check the time. Okay, just a few more minutes on this one. So notice the description is a little bit more involved, I think. When I was setting up these notes, that was one thing that sort of came across to me, is that describing a chemical property takes a little bit more verbiage, and I've tried to make it as succinct as possible with these statements, leaving some things out, really, and I'll talk about that as I write the chemical change out. But the chemical property, you might say, okay, these two gases are explosive, or that the metal and the gas react aggressively. That could be the chemical property, or the metabolism is a chemical property. It's a descriptive form more than anything else. In my view, in my opinion, chemical change is a much more sort of detailed picture about what's going on. For example, if I want to describe hydrogen gas and oxygen gas reacting together, I would do it this way in a chemical change. Now, the fact that I use some of that language over here gives us some information about the chemical changes occurring, but I didn't add that little bit that water is formed, and I guess really this should be a gas since it's an exothermic process. It's going to really be water vapor. This is what used to launch the space shuttle back in the day. You're really controlling it's a controlled explosion to lift off that space craft. And just while I have it here, I'm going to go ahead and balance this equation. So just very quickly, and we'll do full balancing later. Like I've mentioned before, I like to introduce some things early on, even though you're not going to be tested on how to balance the thing. Right? Look at the objectives list, look at the PowerPoints, look at the problems that you're assigned as practice exercises for each chapter. Those are the kind of things you'll be tested on. The balancing of equations you will not be tested on until later. But I want to go ahead and do that just to sort of get us have a longer range view, if you will, things that we're going to do. Because if I look at this molecule, and just real quickly, there's actually one oxygen in this formula. There's no notation, no numerical notation under the oxygen. It's assumed to be 1. It is 1. There is a numerical notation under the oxygen here. It's 2. And so, law of conservation of matter, if I start with 2 oxygen atoms here, I need 2 over there. But and the only way I can do that is to add 2 in the front here. If I add 2 down here, I change the chemical composition. I actually make hydrogen peroxide. That's not what happens in this reaction. All right. So I got to have 2 in front. Notice that now affects how many hydrogens I have present in the formula. 2 times 2, there's 4. I need 2 in front there to then balance out the entire equation. That's the kind of thing that we need to do later on. But for us, it is a chemical change. Hydrogen gas, oxygen gas going to water vapor. Sodium metal, it's a solid, reacts aggressively, yes it does, with something like chlorine gas. Sodium metal reacts aggressively with a lot of things. And any guess what it might form? Something as simple as just the main component of table salt, sodium chloride. Very inert kind of chemical. The worst thing about sodium chloride is it contributes to high blood pressure and heart disease. But it's not like it's going to blow up on you or ignite all of a sudden. Think about this? Where do you keep your table salt versus where do you keep your gasoline for your lawnmower? Table salt's in the kitchen where it's nice and safe. It's not going to explode on you. Gasoline you do not keep in the kitchen. I hope you don't. That's like in the garage, in the shed, outside, out back, somewhere like that. Sodium chloride. Very inert, basically, from 2 compounds that are very reactive. Chlorine gas is very reactive. We'll see examples of that as we go through the class. And chemical change has occurred. This is the diatomic elemental form of chlorine, and this is the elemental form of sodium. I guess I should have mentioned that as well. That's the language that we started working with on the last video. How do I know they're elemental forms? Well, I just have a single element in front of me, HOCl, taken basically directly from the periodic table, as indicating that we have a pure substance in front of us. We have a pure substance here in the form of a compound. It's one molecular formula with 2 different elements in it. And again, just sort of quickly here, and this is supposed to be an S here, just to balance the thing out, I need 2. There's 2 chlorines. There's only 1 here. I need 2 in front. That changes the sodium. I'd have to put 2 over there as well. So there's a balanced equation. Again, chemical change. The thing is modifying during the process. Enzymes metabolize sugars into ethanol. So I'm not going to balance this one because of all the things that, let's see, 12 go on with it. 22. This is the molecular formula for table sugar, or sucrose. Sucrose, that's the U, should be U, sucrose. And enzymes, there's multiple enzymes that carry this out, multiple steps. This acts as a catalyst. It doesn't really factor in. It causes the chemical change, but it doesn't change itself. What do I have here? This is a pure substance, multiple atoms or multiple elements together in one molecular formula. That's a pure substance. That's a very specific chemical formula. And then at the end, it converts into ethanol. Ethanol has, one way to represent ethanol is this. And it'd be a liquid. So alcoholic beverages, active ingredient is ethanol. So the carbons, the 12 carbons, are being ripped apart, for lack of a better phrase, and reformed into this ethanol molecule. And a few other things. I'll just put a few other things here. CO2, gas. If you've made beer or wine, you'll see the bubbling that takes place during that process, that fermentation process. That's the carbon dioxide being kicked off. Water is also kicked off in this process. Yeah, you know what? I'm just going to take that off the table. I'm not certain about that. I just need two things to talk about the chemical change. Because actually, as soon as I wrote that down, I thought, well, actually, water is used to start breaking this thing apart. So I'm trying to think of, anyway, it's too early in the morning to do that. So two products are formed. And again, there's a clear change in the structure. And it doesn't appreciate the fact here that it doesn't have to be this dramatic in a way, meaning graphical. You need to be in the habit or have the ability to interpret the chemical change based on, and this should be a little plus here, based on this conventional notation that we use on the board or the writing on the PowerPoints here. But this is describing a molecule where there's 12 carbons linked together in a particular way with all these other atoms using covalent bonds. We're holding all of these atoms together in a single molecule. And this is much smaller. This only has 2 carbons. And again, this isn't balanced here. So just real quick, like this molecule here, there's a representation of it earlier in that sweet tea. There's sucrose molecule. There's sucrose molecule as a pure substance. Much more complicated than just little old ethanol. But that's where ethanol comes from, or one source of it. Okay, and I know I'm over time. Yeah, I don't like going 21 minutes, but let me just finish 2 more things. Give me another minute maybe, hopefully. So what can we use these physical changes for? Well, we can use physical changes to separate out mixtures. And so mixtures of liquid. Think of corn mash, all right? So moonshine, right? You ferment the corn. It's sort of a bubbly, stinky mash. I guess some might think it smells good. Anyway, if you heat it, what happens is the alcohol fraction, because this is still an aqueous, if we think about this as moonshine, this is an aqueous solution. There is an alcohol fraction within that mixture, and heating it will drive off the alcohol fraction before the aqueous fraction. And in the process, if the heat change, it's a physical change. You got liquid alcohol here, goes into the gas state. It goes through a condenser. This is a simple, I mean, when you first start using it, it's really interesting. And even as a chemist, I still think it's interesting. It's a center glass tube surrounded by a jacket, a glass jacket of water. You run the water through this on the outside of that interior glass cylinder, and it cools off the water vapor. And you see the condensation occurring up here, and then your ethanol or whatever you're trying to purify drips down into your receiving flask. So we're using physical change, liquid to gas, to cause a separation of mixtures. A crude oil is separated through very sophisticated distillation processes. Crude oil is just a massive mixture of all these different hydrocarbons. And the petroleum industry has learned over the century or so of working with this stuff, and even I guess more than a century really, of how to not just distill it and get the different components out of it, but actually start breaking it apart. Some crude oil has really large structures in it and have to be broken apart before you can get things like gasoline or kerosene out of it. So, but they use distillation as a separation process. Okay, physical changes by filtration. We did this, or we will do this in lab, depending on when you're viewing this video, where it's a mixture of a solid and a liquid. Now, an example like this, like wet sand is an example. Muddy French Broad River water with solid particulates floating around in it. If you pass it through a filter, then the solid stays in the filter and you get the liquid down at the bottom. It's another physical change. It's maybe a little bit less involved, maybe a little bit less dramatic than the distillation. You're not like here. You're relying on phase change. You're not necessarily relying on phase change. You're relying on the fact that there's 2 phases already with each other in this sample, and that one phase will not pass through that filter paper. So filtration is another way of separating things through physical changes. And I just wanted to use the last couple of minutes there to talk about those things. And we'll do starting with energy in the next video. Okay, thanks.